A demonstration, perhaps, that you've already seen is when a glass is completely filled with water. Then a cardboard is placed over the glass. It's inverted, and then the hand supporting the cardboard is removed. Atmospheric pressure causes the card to stay in place. This demonstration can actually mislead you regarding the understanding of the next demonstration. Let's add a little food coloring to this water so that it's more visible. Now let's pour that water into a mason jar with a wire screen lid in place of the normal cap. And so the water enters the jar. Once again, we'll fill it to overflowing. We'll place a card on the screen and turn it upside down. But this time, instead of removing my hand, we'll remove the card. The question is, why doesn't the water come out through the screen? Surface tension is the answer to that question. The surface tension of the water around the small holes in the screen. If we tip the jar just slightly, we're able to cause the water to come out through the screen.
By looking into the invisible world of high speed, we discover extraordinary events, even in something as ordinary as a garden pond. These little creatures, water striders, had long been a bit of a mystery. Nobody could work out quite how they could propel themselves across the surface of the water so quickly. They can scoot forward nearly 2 meters every second. And they're achieving something of biblical proportions, actually walking on water, skating across the surface without sinking. Only by seeing what time usually renders invisible to us can we understand what's really going on. And it's got something to do with what's about to happen here. Normally, this is too fast to see. But watch what happens in slow motion as the droplet of milk hits the water surface. Instead of breaking, the water surface stretches, bouncing the milk drop back up into the air. The water behaves as if it has a thin elastic film on the surface. It's called surface tension. And it's this elastic membrane that allows the water strider to stand on the water rather than sinking into it. He's also using that elastic surface tension to catapult himself across the pond at the equivalent of about 600 miles an hour. In coloured water, we can see the force of the strider's legs as they push across the surface. A high-speed artist of the invisible world.
Now, why do we call this force surface tension? To answer that, we will use soap bubbles. A bubble is a thin layer of liquid water floating in the air. Just like a drop, it is shaped as a sphere. But the layer is so thin that we can consider the liquid to have two surfaces and no volume. Therefore, the effects of surface tension are easier to see. Here is a balloon that's about to burst, filmed with a high-speed camera. We can see the plastic shrinking and then converge towards the point opposite to the initial hole. When the balloon is inflated, it is under pressure. All the points on the surface want to get closer to one another. But near the hole, the forces are unbalanced. On one side it stretches, and on the other there is nothing to counter the tension. Now we will do the same experiment with a soap bubble. We can see it shrink like the balloon. It means that the liquid film is also subject to a tension. So now we know surface tension is just a tension force, as in the case of a spring, a rubber band, and a balloon. And it can even move stuff around. This is a metal frame and a rod that we put on the frame. Everything is placed in soapy water. When we take it out, two rectangular soap films are formed on both sides of the rod. We break the film on one side and the rod is pulled to the other side. For the explanation, it's just like before. When there is liquid everywhere, surface tension pulls simultaneously on both sides, and the forces compensate each other. When one of the films disappears, the forces are unbalanced and the rod is attracted towards the remaining soap film. Therefore, surface tension is the force parallel to the surface of the liquid. We can also do the experiment with an inclined plane. Surface tension will manage to raise the rod up the slope.
Water in particular has a very high surface tension. Do you know the reason for this? What creates the attraction between water molecules? In looking at an individual water molecule, we can see the particularly strong attraction between the oxygen and hydrogen due to their opposite charges. Hydrogen has a strong partial positive charge and oxygen a strong partial negative charge. This strong attraction occurs between any water molecules close by. The strong partial charges result in a strong attraction between water molecules called hydrogen bonding. Interestingly, there are creatures that have evolved to take advantage of water's high surface tension. The water strider is a common insect that you may have encountered. What adaptation in their feet has occurred to take advantage of water's surface tension? Think about it.
Of water and a needle, and you took that needle and you very carefully dropped it on the water, it would stay there. And it's not because it's floating. This needle would not be floating on the water. This needle is more dense than water, and we know that if it's more dense, then it should sink. So it's not floating, it's actually just sitting on the surface because there's surface tension. Water is a liquid that's capable of having a significant amount of surface tension. And you know it's surface tension because if you were to come in here and exert a little force down, breaking the surface tension or pushing this needle just below the surface, then it would sink. It would sink like a stone and just drop immediately to the bottom of the cup. So why does water have this property of surface tension? It has to do with the fact that the water molecules within this liquid are attracted to each other. This water molecule can form hydrogen bonds with the other water molecules around it, and it gets pulled toward them. And there's a term for this. We call this cohesion. So the fact that water molecules and other liquid molecules are attracted to each other is called cohesion. But what does this have to do with surface tension? Well, the key is these water molecules would like to bunch together. They want to group together if they can. So what would this water molecule do? I mean, which way is he going to go? How does he pick which one to group with? There's a problem. Here in the bulk of the liquid, he can't decide. Or in other words, let's just say got pulled toward this molecule. Well, it's also getting pulled to the left by all of this. By this one's pulling it back to its original position. This one's pulling it back to its original position because there will be a component of that force that'll point in the direction of its original position, as well as this one to the left. So these are restricted. These molecules here in the bulk of the liquid have too many other water molecules around them dictating where they need to be, because if they tried to get displaced, it'd pull them back to that position. However, at the surface, there's no water molecules above them. These are freer, they're less restricted. So that allows these water molecules on the surface to group together a little better, form stronger, tighter bonds, closer spacing at the surface in such a way that they form a tension that's not present in the bulk of the liquid. Yes, these water molecules down below will prevent them from just grouping into one big clump in the center, but since they're less restricted, they can form these tighter bonds here at the surface, and this allows it to support a pressure from above. So this allows it to support a certain amount of weight, which allows the needle to rest on the surface. Surface tension is due to cohesion between the water molecules at the surface of a liquid, but water molecules aren't just attracted to each other, they're actually attracted to the container too and other materials, and that's called adhesion. So the fact that water molecules are attracted to other materials as well is called adhesion. So what happens is this water molecule isn't just attracted to the other water molecules, it's attracted to the wall, and these water molecules climb the wall a little bit. So that's why you'll see when you fill a container with water or you're measuring an amount of liquid in a small burette, it's not perfectly level at the surface. It actually forms this kind of shape like that. This is exaggerated, but the sides will be a little higher than the middle. So you have to be careful when you're measuring. This is usually called the meniscus, and it's caused by the adhesion, the attraction of water molecules to the container that it's in. This adhesive force, this adhesion force is important. It causes something called capillary action. So let me get rid of this. If you have a container with liquid, or say water, and you took another container, you put it in here like a straw. If you just stick it in, what you'll see is that because the liquid is attracted to the walls of this inner container, it doesn't just stay at this level, it'll rise above. It pulls this up a little bit above the surface level of the water. And if you took an even smaller diameter tube and put it in there, the smaller the tube, the greater this effect, and you'd get this water rising to an even higher level within this tube due to the adhesion to the walls of this container. And the name for this effect is capillary action, which is important in a variety of biological and non-biological examples where fluid is being aided in transport partially by the attraction to the walls of the container or the tube that it's flowing in.
Definition of the meniscus in chemistry terms. All right, so the meniscus is the shape that a liquid takes when we pour it into a container. So let's look at a beaker here made of glass, and let's take the most basic example, water. And if we poured water in here and we let it settle, the meniscus would have a shape like this. And so we've all seen this before, and this is called a concave meniscus, and this is H2O. And then let's take another example. Let's say we had mercury. Pour that in there, let it settle. It would actually form a shape like this, which is called convex. So, why does H2O have a concave meniscus and mercury has a convex meniscus? Well, it all has to do with intermolecular forces. And so, as you notice, both of these beakers are in glass, and glass is made of mostly silicon. So, with water, water is interested in having intermolecular forces with silicon. So it reaches up the side, kind of as much as gravity will allow, so that you can have all this extra interaction between water and the glass. But mercury is not interested in making those connections with silicon. It's not attracted to it. It'd rather be bonded to itself. So it will avoid the glass as much as possible by creating a little convex bubble here and being only with itself. And so that's why you have the differences in shape. But this is both for glass, and let's check out what happens if we have a plastic guy. So let's have water again. We put it into plastic, and it will actually create a completely flat meniscus. So water is neither attracted to plastic nor repelled by it, so it just sits right there. And so one last thing about meniscuses is we have to know where we're going to measure our liquid level in. So let's say we are going to, measure out 10 milliliters of water. Are we going to take the 10 milliliters to be here at the top or here at the bottom or somewhere in between? And the answer is scientists have all decided that we're going to be taking it right at the middle. So for water, it's at the bottom. So we would count our water level at whatever the beaker was right here. And for mercury, convex meniscus, it's also right in the middle. So we're going to have our water level, or mercury level in this case, right here, so at the top. And then if it's flat, it's obviously just wherever it ends. And that's how you read the meniscus.
Why are drops spherical?
Because personally, I'm fond of spherical shapes as compared to squares.
Nah. It is because of surface tension. Surface tension is the property of liquids by which surface molecules of a liquid try to hold the liquid together by acquiring minimum surface area and acting like a stretched membrane.
You know what? Everything just went over my head.
Alright, I'll explain. Inside a drop, each water molecule is pulled with a force by its neighboring molecules. As these forces are equal and opposite, they get neutralized. However, the molecule present at the surface is not attracted outwards. It is attracted only inwards and sideways. Sideways forces get neutralized, but because of the inward force, each surface molecule contracts to form a shape that has minimum surface area, which is a sphere.
If we want to see big round drops, we have to make sure they don't feel their weight anymore. One solution would be to erase gravity by orbiting around Earth. But it's not exactly a common thing to do. Another more practical solution is to put the drop in a liquid of identical density. We fill a tank with water mixed with increasingly more alcohol as we go up. As a result, the deeper we go in the tank, the denser the liquid. Then, we pour some oil, less dense than water, but denser than ethanol. As you know, oil does not mix with water. The oil will run through the layers of water less dense than itself to stop before the layer of water with higher density. At this moment, the oil will form a perfect sphere. This experiment was first performed by Belgian physicist Joseph Plateau in the mid-19th century. But he didn't stop there. Plateau wanted to see what happened if he deformed the drop by pulling on it to create a cylinder. As soon as the surface of the cylinder becomes bigger than the surface of two spheres, the drop is split in two. This is what we call the Rayleigh-Plateau instability, and we can see this phenomenon every day with a tap.
Do you know it will take more effort to separate two glass plates with water between them than when there is no water? Let us try this out. For this we need plastic scale and a dropper. On a smooth and dry surface, place the scale. Now pick up the scale. Notice how easy it was to pick it up. Now place a few drops of water on the surface. Again, carefully place a dry scale gently on the water. Now try to pick up the scale. You need to apply some force to pick it up. We need more force to take out the scale from the water. This is because the surface tension of the water holds the scale and a force is required to remove it from the grip that the water has created.
Hello everybody, my name is Ida. I am founder of Chagrin Valley Soap and Salve. I wanted to share with you an experiment that I used to do with my students to demonstrate surface tension of water and the effect that soap has on surface tension. So let's do some science. I have some water here that I've colored blue simply to make it more visible. Notice what happens as I drop the colored water onto the waxed paper. The water beads up into tiny dome balls and stays that way, and this is due to surface tension. Remember, I explained earlier in the blog that surface tension is a thin film that forms on the surface of a liquid due to the attraction of the molecules. Now let's compare water with another liquid. This time I'm going to use isopropyl or rubbing alcohol. Notice what happens when I drop these drops onto the wax paper. They do not form lovely dome-shaped balls. They sort of spread out all over the wax paper. That's because the intermolecular forces are less in alcohol. The cohesion is less, and therefore the surface tension is also less. Back to my water molecules. I have a number of colored water bottles here, and I'm going to do some playing with my water molecules. So again, notice how as I put the water drops on the wax paper, they all bead up. And again, I've just made pretty colors to have some fun. Now I could take a little toothpick and I can move these little droplets all over the place. I can even combine them all together, and I can do yellow and green. I can do red and blue to make green. I can do yellow and red to make orange. And you notice how even when I maneuver them around with the toothpick, they remain dome-shaped. They keep their shape. What happens if I take a toothpick that has some soap on the end of it? I'm going to take the toothpick and I'm going to touch it. Just simply touching it to my dome-shaped water droplets, they now spread out all over the wax paper. That's because soap is a natural surfactant, and surfactants decrease the surface tension of water and allow it to spread out and become, as they say, wetter.
In soap, molecules have two different parts, one that likes water and one that doesn't. So in a solution, these molecules spontaneously go to the interfaces, where the hydrophilic part can stay in the water and the hydrophobic part can stick out in the air. Remember we said that in water, surface molecules were frustrated because they have less attractive interactions than the ones in the bulk. Here it's different. A soap molecule isn't frustrated because its hydrophobic part wouldn't have created attractive interactions with water anyway. So, from the liquid's point of view, it's easier to create a surface with soap than with water. Soap molecules are called surfactant because they act on surface tension. In fact, they reduce it. And the motion we observed with our particles between two areas of different surface tensions is called the Marangoni flow. This phenomenon was first studied by Italian physicist Carlo Marangoni in the mid-19th century, but it's still an active research topic, as you'll see in the next videos of the Lutetium project. But just to pique your interest, let's show you another Marangoni flow. This is a piece of camphor. Just like soap, it's composed of surfactant molecules, but unlike soap, these molecules are also very volatile. That's why we can make camphor boats. We stick a small piece of camphor on a plastic boat, we put it in the water, and it is propelled by a Marangoni flow. But, since camphor vaporizes in its wake, the surface of the water becomes pure again after the boat passes. Therefore, a difference in surface tension between the front and the rear of the boat is always maintained. That's why it can be propelled as long as there is still camphor to be dissolved.
Few practical applications of this. One clinical: if there's bile present in urine, you could detect its presence because it lowers the surface tension of urine. So it gives you a test of whether the liver is metabolizing things the way it should. Another application is if you go camping and you're in the tent, it's raining, and the tent gets raindrops on it. Most tents will keep the water from seeping through, but you're going to be tempted. You're going to be sitting in here, you're going to be like, that looks cool, and you're going to touch it, but you're not supposed to touch it because as soon as you touch it, you may break the surface tension. And once you break the surface tension, that water's dripping into your tent from that spot that you touched it, and you're probably not going to have a good night. So resist the urge to break the surface tension on your tent if it's raining out. And when you wash your hands, when we use detergents, if you washed your hands with just regular water and that's it, sometimes the surface tension's too great. These water molecules are too bound to each other. They form too big of a clump. It doesn't look like it. It looks perfectly smooth. But on a microscopic level, the water's not as diffuse as it could be. That's forming these clumps because the water has cohesion and it joins together. But if you add a little soap to the scenario, that breaks the surface tension. It lowers the surface tension, which means these water molecules don't clump together as much, and if they're not clumping together, they can get into the small cracks, which kicks out the dirt in your hands, and this water is better able to penetrate into the smaller cracks and get where it needs to go.